Welcome, everyone. In this session, we have Dr. Shay Strong, VP of Analytics at ICEYE, presenting Woes and Musings of a Once-Astronomer and SAR Newbie. What is SAR and Geospatial Data Science? As a quick note, please post your questions to the Q&A box instead of the chat. Off to you, Shay.
Thank you. Hello, everyone. It's so nice to get a chance to speak with you. It's a little dark on my side. I'm in Helsinki, Finland, so we're at about, I think it's 40 a.m. So you'll have to bear with me, and hopefully I don't say anything completely ridiculous. Let me make sure that I am seeing. All right. I think we are good to go. I'm going to launch 2 polls. I think just take them at your leisure. I am not entirely sure how successful they will be, but I'm just kind of curious about who is attending and maybe what your experience is with SAR and or geospatial data science. So I wanted to just explain to you first, this image here that you're seeing, this is actually a colorized SAR image. So SAR, if you're not familiar, it's synthetic aperture radar. And we'll talk about a little bit more about the physics there in a second. But essentially what you're seeing is a radar return that's transformed into an image. And the different colors here represent different times of day. In this case, it's 3 consecutive days. And so red is one day, blue is another day, yellow is yet another. And if we add them all up together, they become white. So essentially anything in white here is unchanged. Combination of intensities, and anything that has a specific color, of course, is just attributed to that day. The cool thing about this, I mean, perhaps not cool for the people involved, this was a flood in the UK back at the beginning of the year, but the cool thing here in general with this technique is like you can definitely see as a function of time some of the specific changes that are happening. So looking at a river here, you can see the river kind of breaches this area and floods this agricultural field here. So a lot of cool stuff going on here, a lot of physics. Right. So a little bit about me. My background was not data science at all, nor was it SAR. Originally, I went to school for astronomy, and I worked, or I got my original degree in physics at the College of Charleston, and then did a couple of internships at a variety of observatories, studying things like pulsating variable stars, and looking at different galactic clusters. And then I went into grad school to get my Ph.D. at the University of Texas at Austin, where I focused a lot on Saturnian climatology, so developed some physics-based climate modeling for gas giant planets, and also worked on some instrumentation that was on board a stratospheric aircraft. So started diving into instrumentation and technology, but really focused in, I would say, things outside of Earth, for sure. When I graduated with my PhD, it became pretty obvious that it was going to be hard to find a job in astronomy. And this was, for many of you, probably quite some time ago. So before data science was a thing. And that it was pretty unique. But I managed to get a job at Johns Hopkins University Applied Physics Lab in Maryland, working largely in defense. So working on spacecraft development and design in the defense world. So being deployed to Hawaii for quite a bit of time, working on ballistic missiles and looking at some of the physics of their signatures, and doing a lot of field testing. This is a little RV here where we had LiDAR set up on it. I also got to work on the Solar Probe Plus mission, which has since been renamed. This was a NASA mission that has sent the probe closest to the sun that any instrument has ever. After a period of time, I left the university there and joined as the first ever data scientist at a company called OmniEarth in Washington, D.C. And this was pretty unique for me. This was back in 2014, which I would say is the heyday of data science. And there was a lot of really cool technologies coming online. The intent of OmniEarth was to launch a satellite that observed the Earth every day, everywhere. And we never actually got to the point of launching satellites, but what I was able to accomplish with my team was creating a lot of scaled computer vision and deep learning applications to do semantic segmentation against satellite imagery. So being able to identify things like flooded regions or impervious surfaces, or looking in general at vegetative changes and urban growth. The company was we did pretty well on the computer vision side, and ultimately got acquired by a company in Seattle, EagleView. And this was very much focused more on applying deep learning applications to insurance use cases. So looking at roof damage, for instance, scaling the identification of storm damage, and being able to essentially put it on a map. And that is fundamentally what geospatial data science is being able to ultimately put analytics on a map to some degree. After my stint there, I joined Rebellion, which is also part of it is based in the Seattle area, and kind of going back into the defense world, looking at automating some drone technologies and some computer vision applications for detecting threats and targets. And it was interesting, but it was very short-lived, because after about 5 months, I was offered an opportunity to join ICEYE as the VP of Analytics. And ICEYE, based in Helsinki, Finland, builds a constellation of small SAR satellites. So we'll talk about that here shortly. ICEYE was founded just a couple years ago, actually, but we are currently at 220 people. The biggest component of our org is in Finland, but we also have a Poland, UK, and a US office. We were the first company in the world to launch these special SAR satellites that were less than 100 kilograms. So kind of on the size of maybe a large dishwasher. So this was pretty novel. And we've already demonstrated and launched 10 satellites by early this year. And the cool thing about SAR is that not only can it see day-night, so you no longer need the light of the sun to observe down below at the Earth, but you can also get these really beautiful perfectly repeat images consecutively over several hours or over several days, as the case may be, and you can look at all the time change. So this image is a SAR image. This was, of course, the infamous Ever Given that was stuck in the Suez Canal back a couple weeks ago. And just to give you a sense of kind of what you're looking at. Of course, geospatial, we're looking at the Earth. This is now you can see various boats here kind of waiting to pass through. And then the zoom in here, you can see the vessel itself. All right, so then in terms of where is SAR in the electromagnetic spectrum, this is probably not what you guys expected when you joined this talk, but really SAR and synthetic aperture radar tend to operate in the microwave domain. There's some really interesting history here, but these specific frequency ranges or wave bands have very hard to remember designations, all done on purpose. It was originally, a lot of them were developed during World War I and then later in World War II. And the intent was so that it wasn't easy to remember. But the ICEYE constellation works in X-band, so this is kind of the wavelength range that we operate on. And you can see, of course, probably to no surprise here, this is a small component of the electromagnetic spectrum where, of course, visible light is what we see, and then anything smaller is kind of on this size, going down to the atomic level, and then anything longer wavelength goes out. And so if I were to kind of oddly map where my work was performed as a function of the electromagnetic spectrum, they kind of bounce around a lot in the visible world, a little bit in the infrared, and then now finally in the microwave. So I still have a lot left to understand. Then, so, what is remote sensing? Maybe some of you are relatively familiar to this, but ultimately remote sensing is a process of detecting and monitoring physical characteristics, typically of the Earth, from a distance of some sort. Here, this picture here, I just learned about this actually when I was putting together the talk, but there was an inventor, a German inventor, Bronner, who was kind of the first to prototype this by putting little cameras on top of pigeons in 1900. And so you can see actually literally a bird's eye view of, I suspect, someplace in Germany looking down. Interesting angle. But from a cloud compute perspective, we talk about cloud compute as really fundamentally being someone else's machine or somebody else's computer. Well, remote sensing is fundamentally someone else's distant sensor looking. And so SAR, I kind of talked around it. It's relatively complicated in terms of physics, but there's an interesting difference that SAR is unique, or that is unique to SAR in particular. It's an active sensing technology as opposed to a passive sensing technology. So in a passive sensing technology, just camera, could be like your iPhone camera, you take a picture, the brightness of that picture or what you see is very much dependent on what's being illuminated. But with an active system, the radars actually send down a signal and via a pulse is transmitted, and then collects back what's scattered. And so in a way, it's not that dissimilar from how a bat uses echolocation. A bat uses something like ultrasound, but radars are, of course, using these microwave wavelengths. And so from that backscatter, so from scattering back the signals that you see as a function of location on the Earth, you can build two-dimensional and three-dimensional images. One of the interesting things is that, like, until recently, this was really hard because the resolution, so the ability to resolve objects on the Earth, scales with wavelength over the size of the antenna. And so, you can have a really small antenna to get really high resolution, see very fine detail, but you can't necessarily move that around pretty quickly. You can only cover a small region. And if you build a really large antenna, you get super low resolution. So the really novel thing about synthetic aperture radar is that you can essentially transmit a bunch of pulses and integrate over that signal as the satellite orbits Earth and collect all that information. And then you get this kind of synthetic aperture that has collected all this signal. And in a way, for the ICEYE's X-band satellites, if we wanted to get like 1 pixel mapped to the ground in 1 meter of resolution, you would need something like a 21-kilometer antenna. And so, by comparison, here's the little Eiffel Tower, and that's just totally unrealistic. So until like technology has just kind of recently modified this, it was pretty hard to do. But the beautiful thing, again, because you control the pulse, you control the physics, you can look through day and night, you can look through clouds, control this energy source. So and then just a quick demonstration of course, sending a pulse from the satellite as it moves across a target. So the little satellite's the white dot, the target is the red dot. And you can see, of course, the lovely Doppler effect. Satellite moves across this target, you get essentially different frequencies of information moving back. And so all of that has to be corrected, and it kind of contributes to the way. There's a lot of SAR open source tools, but it's a bit challenged by the fact that it's a mixed bag of a lot of academic insights. And I think there's been some really clever groups recently with EO College and some others that have reduced the barrier to entry. But unfortunately, a lot of capabilities are locked into kind of static PDFs and just not maybe data science friendly usability. And so ICEYE is trying to work towards democratizing and making SAR a bit more accessible through contributing to new tooling and then also through research contributions. What I wanted to demonstrate here is, like, fundamentally, whether it's SAR or any kind of geospatial data science, always a layered stack of information that goes on. You have some foundational layer. In my case today, it's Sar image, but essentially with any geospatial problem, you have to layer that with supplemental data, where are the buildings, where are the roads, where are the trees, etc. And then you'll have maybe an algorithmic layer of a variety of different things. It could be deep learning extraction. It could also just be maybe more conventional computer vision capability. And then you have the compounding component of, like, you got to make this scalable. The great thing about deep learning when it's fused with geospatial is that you can scale a lot of processing. So you can scale petabytes of image processing with using a deep learning algorithm. So there's a lot of potential there. But then, like with any engineering problem, you have deployment issues that you have to figure out. How are you going to sustain this and build this and create some kind of, and then you got to quality control it. I think the unique thing about geospatial data science is that it can all be validated. Somebody can drive to a location and confirm whether or not what you did was correct. So it definitely keeps you honest, and it's also the bane of our existence in the geospatial domain. With SAR, a couple of cool things is that you have, you can control how the orientation is for your acquisition, and that can really impact the types of signals that you see. The other thing is that there's physics available using a SAR sensor that you wouldn't necessarily see with an optical. So you can learn things about the material properties or their dielectric constants, for instance. Dig back into the recesses of your chemistry or your physics from high school, college. So there's a lot of really cool stuff here that is not really exploited. I think we're really scratching the surface largely. And SAR machine learning itself doesn't essentially exist natively. I mean, today what most people are doing is applying a lot of standard computer vision, kind of that visual red, green, blue application to SAR, but it doesn't always map so well. And so thinking about geospatial machine learning, there's kind of components. Of course, there's your machine learning component of learning about all these different capabilities and leveraging some of these types of libraries. You have a raster component, which is the images, it's the pixels themselves, and a lot of really foundational libraries that leverage that. And then this vector component that is, where are things? What is the latitude, longitude coordinates of the shapes of? And fundamentally, that's it. Like geospatial data science is using a combination. And then, like I mentioned, it's pretty easy to validate. It keeps you honest. And yeah, SAR is just a bit complicated on top of that. So to show you some examples here, like we definitely leverage SAR quite a bit for flood analysis. So in Australia, we performed machine learning applications to evaluate approximately 10,000 square kilometers of coverage here to look for some of the floods recently. And we can also do things like object tracking and identification and heading in the case of vessel. Another cool application is just, yeah.
Shay, sorry, just to let you know, we have a couple minutes left if you want to leave any time for questions.
Absolutely. So just one more minute to close out. There's some cool things that SAR has been used to try to make it look like visual. So using generative adversarial networks, and then mapping things like forest vegetation and deforestation. So this is just my last slide. Again, another pretty one that shows vessels moving in different ways. And I'll just end there to make sure that I have an opportunity to hear any questions. Polls. Wow, a lot of people never have used geospatial data. And nobody, 88% of you did not know what SAR is. So that's awesome. Hopefully you. All right. But please feel free.
Because of the lag, it might be slow for questions to come in. So we can give people a few more seconds to chime in. But thank you so much. That was really interesting.
Yeah, of course, my pleasure.
And full of cool pictures.
I'm a pretty visual person. The pictures go a long way for me.
Yes.
Right, is SAR your favorite kind of data to work with? I don't know, it's really hard. I'm still just getting my head around it. I feel like every day I don't. But it is pretty cool, and I think there's a lot of new territory there. Can you explain the GAN and GEO? So the generative adversarial network is often used to maybe some of the more obvious use cases, right, is you take a picture and you can morph that picture into something else. So you can take a selfie and morph it into a Monet, whatever. In the case of satellite imagery or geospatial applications, you can use it to create new training data, for instance. So you can leverage it to create synthetic training data about an event. But for SAR, you can change the style of the SAR from radar look a little bit more visible. So instead of looking at a signal like this, you can see something that maybe your eyes are a bit more familiar to. I think I answered.
And that takes us to time. So thank you so much